Hello everyone, welcome to my channel. In this lecture we will discuss about the production of toluene from n-heptane. In this lecture we will discuss about the production of toluene from n-heptane using chromium catalyst. So toluene is produced from n-heptane by dehydrogenation over a catalyst Cr2O3. The reaction for the same is given below. So n-heptane, this is n-heptane, 1 mole of n-heptane give us 1 mole of toluene and 4 mole of hydrogen in this reaction, and this reaction is taking place on the surface of catalyst, which is made from chromium oxide Cr2O3. In this process, toluene is produced along with hydrogen is shown in the reaction. In this reaction, the process flow sheet show the conversion of n-heptane to the toluene using catalytic reactor on the reaction. So toluene is production process is started by heating n-heptane. So first of all, we will heat the n-heptane from 65 degree Fahrenheit to 800 degree Fahrenheit in a heater. Then it will feed to a catalytic reactor which operates isothermally, and 15% conversion of n-heptane will take place in the conversion reactor. The effluent from the reactor will then cool to 65 degree Fahrenheit, and after cooling it will feed to separator. So the separator is nothing but it will be a flash column. Assume that all the unit operate at atmospheric pressure. Specify the molar flow rate, species flow rate, and other property. So we will determine the molar flow rate and other composition and other profile in this lecture. So in this lecture we will discuss about the separator and reactor combined. So first of all, open the Aspen HYSYS. This is Aspen HYSYS, and click on new. New window will open. So click on new. So this will take some time. So this is the component list. Click on add and add the component. So there are 3 components: n-heptane. This is n-heptane. Click on add. Then click on add toluene. Add, then hydrogen. So hydrogen, we can add. So these 3 are the component. Now go to the fluid package. In the fluid package, click on add and add a fluid package. So mostly for hydrocarbon we are using the Penn-Robinson equation of state. So click on the Penn-Robinson equation of state. So this is okay. The green bar shows that all the property, all things are okay. So then go to the simulation. Click on simulation. So a simulation window will open. In this simulation, first of all, we will heat the n-heptane to some specific temperature. So click on heater, drag and drop it. So this is the heater. Okay. Then after heating, it will go to the conversion reactor. So click on reactor and then click on conversion reactor. So this is conversion reactor. Drag and drop. This is the conversion reactor. Okay. Then after the conversion reactor, the product from the conversion reactor will cool to some temperature. So we will select the cooler. So select the cooler. This is cooler. Drag and drop the cooler. After cooler, it will go to the product from the cooler will go to the separator, to the flash column. So then it will go to the separator, and here this is a flash column or simple separator. So click on this one, drag and drop. So these are all the. So this is the now. This is okay. Now this is click on the heater. So this is inlet. So I will this is the feed, and this is the product. This is the product, and the energy we will put the energy. So okay. then the product from the heater will go to the conversion reactor. Click on the conversion reactor. The name of the conversion reactor is this is okay. You can change the name, but I am not changing it. So here you can the stream. So this is the product. The product from the heater will go to the separator. Okay, and the overhead vapor. So this is vapor, and this is the liquid. This is the liquid. So it shows that require a reaction sheet, so we will add reaction after certain time, after some time. So close this one. Okay, this is the reactor, conversion reactor. Now the vapor, the product from the conversion reactor will go to the cooler, so it will cool down. So click on this one, and we will input. So the vapor from the conversion reactor will cool to some temperature. So this is the cooler, and this is the cooler outlet. And the energy for the cooler is CE, cooler energy. So unknown delta P. So okay, now this is the cooler. So now click on the flash separator, and this one, the product from the cooler outlet will go to the flash separator, and this is the vapors, and this is the liquid from flash separator, and vapor from flash separator. Okay, close this one. So this is the vapor, and this is the liquid. Now this is the energy stream. So this is the energy stream. Now we will go to the property, and here we will go to the reaction, because it shows that 15% n-heptane is converted into the toluene in the conversion reactor. So 15 mole percent of the n-heptane is converted into the toluene. So we will close this one, and then add. So click on add, and here add a reaction. This is a conversion reaction, so click on conversion reactor, and click on add. So close this one, and double click on reaction number 1. This is reaction number 1. So in this reaction, 1 mole of the n-heptane converted into the toluene, 1 mole of toluene, and 4 mole of hydrogen gas. So the 1 mole per reactant we will put the negative sign. 1 mole of toluene give us 1 mole of n-heptane give us 1 mole of toluene, and 4 mole of hydrogen. Okay, the balance error is 0. Okay, now 15%. So the reaction phases were all, and the base component is n-heptane. Okay, the C0, this is the conversion formula. So C0 plus C1 into temperature and Kelvin plus C2 and temperature to the power 2. So the C1 and C2 is 0, and C0 is 15% conversion of n-heptane is taking place. So put 15. Now this is okay. Close this one, and click on add to the fluid package. So now we will add our reaction to the fluid package. Our fluid package is nothing but it is the Pin-Robinson equation of state. So click on add to the fluid package, and click on add set to the fluid package. So it is okay. Now go to the simulation, and here this is the feed. So the feed, everything the feed product, that the pressure everywhere, the pressure is 1 atmospheric pressure, and the feed property is given to us. So click on the feed, and here the feed name, this is the feed name, and the temperature of the feed. So this feed will go to the heater, and the molar flow rate of the feed is, suppose it is 100 kilogram mole per hour. So it is okay, and suppose it is a pure n-heptane. So pure n-heptane, the mole fraction, so this is the mole percent will be 1. Click on this one, and the mole fraction of n-heptane is 1. Okay, click on OK. Now go to the condition, and here the n-heptane is heating from what temperature? You can see the n-heptane is the n-heptane catalytic reactor, the production taking place. So n-heptane is heating from 65 to 800 degree Fahrenheit in the heater. So 65 to 800 degree Fahrenheit, 65 degree Fahrenheit, 65 degree Fahrenheit. This is 65 degree Fahrenheit. Now this is okay. Everywhere the pressure is 1 atmospheric pressure, so the pressure is 1 atmosphere. So this is okay. Now close this one. This is okay. Now this is the click on the reactor. Now click on the reactor, and here require a reaction sheet. So go to the reaction, and here click on sheet, reaction sheet number 1. So this is okay. Now this is the basis, this is the conversion. So C1 and C2 are 0 0, so this is 0 and this is also 0. Okay, now this product stream is click on this one, and the feed is heated from 65 to 800 degree Fahrenheit to 800 degree Fahrenheit. So 800 degree Fahrenheit. Okay, now click on the heater, and here unknown delta P, so there is no pressure drop in the heater. So click on the parameter, and the delta P is 0 kilopascal. So that is okay. Now close this one, and here now go to the this one. The product from the this one, the conversion reactor will go to the cooler. So it will cool to some temperature. So it will cool to the effluent is cooled to 65 degree Fahrenheit and feed to the separator. So it will cool to 65 degree Fahrenheit. So it will cool to 65 degree Fahrenheit, 65 degree Fahrenheit. So 65 degree Fahrenheit, 65 degree Fahrenheit. Now it shows that unknown pressure. So the pressure I will put to close this one. You can put here, or you can double click on the cooler, and here unknown delta P. So that go to the parameter, and the delta P across the cooler is also 0. Okay, close this one. So now this. So this is the now we will show that what will be the molar flow rate of the what will be the molar flow rate. So here you can check the cooler, the heater duty. So double click on the heater, and here you can check the heater duty. So go to the parameter, and this is the delta T across the heater, and this is the heater duty. You can check this one. This is the rating, and this is the worksheet, the feed product energy, the performance, the delta P, the dynamic. So this is the all about the heater. The delta P across the heater is this one. Overall this one you can check this one, the hold up. So close this one to the heater duty. Now the cooler duty you can check. Double click on the cooler, and here you can check the cooler duty. Go to the parameter. This is the delta T across the cooler, and this is the cooler duty, 9.97 multiplied by 10 raised to power 6 kilojoule per hour. You can also check here. You can see this is the power of the cooler. It is 2772 kilowatt, and the power of the duty of the power of the heater is 3790 kilowatt. So now you can check this is the separator. Here you can check the separator. This is the vapor. Now click on this vapor from the separator. Here you can check. Go to this one. Go to the composition, and here click on basis, and click on mole flow. So click on this one. Now here you can check the molar flow rate. So the vapor molar flow rate from the molar flow rate of the n-heptane from the flash separator is 2.4044 kilomole per hour, and this is 0.36 of toluene, and the hydrogen is 59.91 kilomole per hour. So this is the molar flow rate of the toluene, hydrogen, and n-heptane from the flash separator. Here you can also check the molar flow rate of toluene, hydrogen from the flash separator. So go to the composition, and here you can check, go to the basis and change the basis from to molar flow. So here you can check the molar flow. So 82 kilomole per hour of the n-heptane in the liquid, 14 kilomole per hour of toluene, and 0.083 kilomole of hydrogen is coming out from the bottom of the flash separator. So here you can check. Now you can also plot the profile. For example, this is the heater, so double click on the heater. So click on the heater, and here you can go to the rating. This is the design, and this is the rating. This is the worksheet, and this is the performance. So go to the plots. So from the plots, this is the temperature versus the pressure of the heater. So the temperature as the temperature increases, the pressure is not changes in the heater. So you can check the, suppose this is the temperature, and now I am changing it to the enthalpy or the heat flow. So that this is the heat flow. So sorry, this is the temperature, the temperature versus pressure. So on the y-axis I am changing to the heat flow. So this is the, as the temperature increases, the heat flow also increases in the heater, and it is in the kilojoule per hour. So this is the plot. You can also plot the table. For example, click on the table. This is the temperature, pressure, enthalpy, etc. So this is the table. And now close this one, and the cooler, you can also check the cooler profiles. For example, go to the worksheet, and here this is the composition performance. Go to the plots, and this is go to the, suppose go to the heat flow. So this is the heat flow across the cooler. So now close this one, and this is the molar flow rate. The molar flow is 62 kilogram mole per hour from this in this vapor, and the molar flow rate of the liquid from the flash separator is 97 kilogram mole per hour. So this is the liquid. Again, this is 00, and this is the conversion reactor. This is the heater. This is the feed. So here double click on the conversion reactor. Here you can check the reactor, and this is the rating, and this is the here you can check go to the dynamic, hold up, and these are the various other things. So go the heat loss. Okay, this is the heat flow. This is the heat flow in the heater, in the conversion reactor. So this is all about the. Now you can also plot the go to the workbook, and this is the vapor fraction of the feed, product, vapor, and liquid, cooler outlet, vapor, and liquid from the flash distillation from the flash column. So these are all about the temperature of the feed, the product temperature, the vapor temperature, the liquid temperature, the cooler temperature. So these are all things. Here you can also go to the setup and add some other thing. Here click on add and add some other things. So close this one, and close this one. So close this one, and this is the go to the main flow sheet. So this is the main flow sheet. You can also check on the report, click on the report, and you can also create the report. So create a report, click on create full report. So sorry, listen. So this is the full report, and this is the template. So click on create and preview, click on preview. So you can see the report of your process. So it will take some time. So it will take some time. So this is okay. Put insert data sheet. Okay, click on preview. So here report, click on create and click on preview. So here report will also occur, but our main topic was how can we determine the molar flow rate of the vapor stream and the liquid stream from the flash separator. This was all about the reactor, separator, cooler and heater. This is the heater duty here. The heater duty is 9.97 kilojoule per hour, and this is the 1.3. So this cooler duty is very high. So you can recycle this stream to preheat this stream. So you can also add some heat exchanger in this place in order to use this order to use the heat of this place. So thank you very much for your attention. If you are new to the channel, please like and subscribe. Thank you very much.